Hi, so we'll continue to talk about shell sort, but this time using different gap sequence. So we have seen that having the gap each time, it can sometimes create problems for certain type of data. Right? And the reason for that is it results in kind of elements, groups of elements or sublists that kind of never interact with each other, never move against each other until the very last insertion sort. And therefore, the last insertion sort, it might have to do with a list that is very, very unsorted. And we know when that happens, it's it's going to take quadratic time. So, and that's actually this kind of having the gap. That's what Shell's original algorithm used, right? In case of a power of the number of elements in the list is power of 2, so it's basically 1, 2, 4, 8, 16, so on and so forth. Now, that's one choice of gaps, but there is nothing in the algorithm itself that says the gap must be that way. And over the years, people actually come up with many different gaps. So one such gap sequence was invented by Hibbard a few years after Shell's invented his sorting algorithm. And this gap sequence is actually very similar to Shell's gap sequence, except that instead of power of 2, it's power of 2 minus 1. So for a list with power of 2, number of elements is 1, 3, 7, 15, so on and so forth. And this very elegantly solves the problem of Shell's gaps because it does not result in sublists that do not interact with each other until the last insertion sort. And the intuitive reason for that is that these numbers are relatively prime. And that's certainly not the case with Shell's gaps. If you look at these numbers, they are as far away from relative prime as possible. They're multiples of each other. Okay, and so now it can actually be proved that the shell sort using Hibbard's gaps, it is on the order of O of n to the 3 halves power. So it's better than quadratic. And let's see it in action. Now, in order to use a different gap sequence, I'm actually going to modify the original implementation of shell sort, and I'm going to factor out the gap sequence generation from shell sort and into a, what else, Python generator, which is just kind of perfect for this kind of application. So I'm going to write a generator, Shell's gaps, given the length of an iterable or a list. Now, so again, the first gap we're going to we'll start with would be length divided by 2, and as long as gap is bigger than 2, I'm going to yield the gap, and then the next time we need another gap is we're going to divide the gap by 2. Okay, so this is a generator, and the shell sort now is going to take a gap generator or gaps generator. It's going to default to shell's gap, and the way it's going to work is now it's going to be in a for loop, right? So for whatever this gaps generator, we're going to give it the length of the iterable, and then it's going to give us back a gap, the gaps in kind of a sequence, and then we'll just call insertion sort in with that gap. And obviously the advantage of writing it this way is if we want a different gap sequence, we just write a different gaps generator, pass it in as a parameter, and we don't have to change shell sort itself. And that's exactly what we'll do next. And so we're going to write Hibbard's gap sequence generator, which is basically shell's gaps minus 1. So we're going to actually use shell's gaps. Now, in my testing, I actually find a few corner cases that I don't know how to elegantly handle inside the loop itself. So I have to kind of special case them before the loop and after the loop. So what the edge cases are is that if the length is either 0 or 1, we know we don't have to do insertion sort, so we are done right there. And then occasionally, well, actually for length of 2 and some other lengths, this loop here actually will not yield the final gap of 1. So that's why I have to kind of check, okay, is the last gap we yielded, was it 1? If it's not 1, we have to yield 1, because we absolutely need 1 to ensure the complete sorting of a given iterable. And now to kind of implement shell sort using the Hibbard gaps, well, I wrote I wrote a different function just so that it's distinguish it from the original shell sort using the shell gaps. And basically, shell sort Hibbard is shell sort, but we set the parameter, the gaps parameter, to the Hibbard's gaps generator. And that's what I've already written out here: shell's gap, Hibbard's gaps, and shell sort with the gaps parameter, as well as shell sort using Hibbard's gaps. So as usual, once we have an implementation, let's test it. And the way I'm going to test this is, given that we already have a shell sort test case that kind of measure its performance using different gaps. Now I'm going to create a shell sort Hibbard test case that inherits from shell sort test case, so that it will also have the advantage of running these same set of tests to measure the performance of Hibbard. And if you kind of look at the results that we measure using Hibbard's gaps, compare that with using shell's gaps, it's kind of astoundingly fast. If you look at the last one, it's so much faster, even though it's the same shell sort algorithm. As a matter of fact, in the worst case for shell's gaps, but using Hibbard's gaps, it's even faster than the random data using shell's gaps. So anyway, I hope you kind of see the moral of the lesson is that the choice of the gaps for shell sort is extremely important for the performance of shell sort. And in this week's assignment, you are actually asked to kind of investigate and experiment with other gap sequences.